Okay, problems 198 through 202. On 198, which axis is domain about, the x or the y? Well, it's important to me that you understand that domain is about the x's, which is also the inputs of a function, and which is also the independent variables. Go down there. And the range is about the y, which is about the dependent variables. And they're the outputs. Outputs. Okay, so keep domain and x together in your head, and keep range and y kind of go together in your head. All right, moving on. 199. Identify and label the roots of the quadratic that's graphed. The roots are the places that it touches the x-intercept. And if you think about this, it makes sense that when we have our equations, we set them equal to 0, because we'll have this quadratic equation, like let's say x squared plus 2x minus 5 or whatever, and we set it equal to 0. Normally it's y equals something to get a graph of x and y, okay? Or y is the same as f of x, right? So I could put an f of x here. But if we set it equal to 0, we're basically setting y equal to 0. And if you're setting y equal to 0, you're getting the x-intercepts. You get that? The x-intercepts are where y equals 0. So when we're trying to find these, when we're trying to find the solutions and the roots and the zeros, those are all kind of words for the same thing. They are the places that the x-intercept. Okay? And that's why we set y equal to 0 when we're solving a quadratic like this. It's because we want to try to find the x-intercepts. Okay, so identify the label and label the roots of this quadratic. Well, here they are. This is one root. Here's another root. Now exactly where they are, it looks like that spot right there is at 0, 0. And over here, if I look real close, it looks like that spot is trying to tell me -3, 0. Okay, so that would be my 2 roots of this quadratic. Problem number 200. Identify the minimum degree of the polynomial graphed below. Well, when we learned about these, we called something like this. It looks a lot like a bounce. Okay, that gives us a double root here. Okay, so that one counts for 2 roots. Okay, it's either that, or if we zoom in really close, maybe this thing cuts through and then comes back down again. Then it's 2 single roots. But either way, this area is worth 2. It's either a bounce, which is worth 2, or it's 2 cut-throughs, which is worth 2. Okay, so the multiplicity so far is 2 for that. That's definitely a cut-through. It's the way that the function interacts with the x-axis, and it looks like it's cutting through it, and that's worth 1. So this is degree 2 plus degree 1 means it's a degree 3, and that totally makes sense that it's degree 3, because a degree 3 would have end behavior that's going in opposite directions, because an odd degreed function would go in, the ends would go in opposite directions. Okay? The other thing that we could say about it is possible that it is a higher degree than 3. It could be a degree 5 or a degree 7, but it's at least a degree 3. Why could it be more than the 3? Even though we all counted it out here, it was 2 for that and 1 for that made a degree 3. The reason it could be more than that is if this had imaginary roots, we wouldn't be able to see them. They would not be on the graph in any way that you can like guarantee that you can see it. All right, so this could be degree 3, but it could be that there's imaginary roots, like, and they always come in packages of 2. So if this has got imaginary roots, it's possible that those would make it a degree 5 or a degree 7 or a degree 9. And so basically this is a degree 3 at minimum, okay? So you count up bounces and cut throughs, and there's one other kind that's not a bounce and it's not a cut through. It's the triple root, and that looks kind of like the graph of y equals x to the third. It goes kind of like this, all right? That's a triple root, and so if you ever see one of those, that is worth a degree 3 all by itself. So if I had that and then it somehow came around and cut through again, then my function would have to be degree 3 plus another cut through makes it degree 4, and that would make sense because the end behavior is it's going in opposite directions from each other, and therefore, or sorry, they're going in the same direction as each other. They're both heading down like this. Degree 4 would work for that. All right, so there's a little discussion of how you can tell what degree you have based on the look of the graph, and all you really look for is how it touches the x-intercepts. If it bounces like this, or whether it cuts through, or whether it makes that kind of S-shaped cut through, the swerve some people call it, or a snake other people call it, or just the thing that looks like the cubic, like that, that kind is worth a triple. All right, and then you just got to remember also that there could be other roots that you can't see, but they're always going to come in packages of 2, and so it's either degree, this one from the original problem is either degree 3, or there's also these imaginary root possibilities, so it could be degree 5 or degree 7, etc. All right, problem 201. The y-intercept is found where x equals 0. And if you can just try to remember this, the x-intercepts are found where y is equal to 0. Okay, so it's kind of a logical corollary that if the y-intercept is where x is 0, the x-intercept is where y is 0. And that's really handy because then if you're given an equation like this, y equals x to the third plus 2x plus 5, and I want to know its y-intercept, I just have to plug in x is 0. I stick in x is 0, and then I will find the y-intercept is y equals 0 plus 0, y equals 5. Okay? Or if I want to find the x-intercept, the x-intercept is where y is 0. So if I had this equation and I wanted the x-intercept, I set y equal to 0. And if I can solve this by maybe graphing it or factoring it, if I can find what x is, then I've found the x-intercept, because the x-intercept is where y is 0. It's really powerful to understand that. All right, next, sketch a graph of exponential growth. All right, so if I have a sketch, all I need is my x and y axis here, and exponential growth, generally speaking, it starts out at a low number, and then it grows in a curve that goes up, increasing at an increasing rate. Okay, that's exponential growth. If it was just increasing at a flat rate like this, that would not be exponential growth. That would just be constant growth. To get exponential growth, it has to not only be increasing, but it has to be increasing at an increasing rate, meaning that at the beginning it's going not very fast, not very steep, and at the end it's going faster, quite a bit faster.